Okay, let me show you the unusual tuning feature of the Radio Shack DX390 shortwave receiver. I noticed this, and it took me a little while to figure out what was going on. But I have the radio tuned up now. It's on 75 meters. There's a QSO going on at 3182. I'm sorry, 3812. And I'll just show you. I have it tuned in. Let's take a listen.
Yeah, you can also get a big chunk of aluminum.
You can see it's tuned in.
From the shop tower across.
And I've got the BFO control here almost at full vertical, a little bit to the right. But watch what happens. Go down 1 kc. Now I can still tune them in. Go down, no.
Chuck and I were going
Same. I'm just moving the BFO control.
Yeah, they sell French.
Can't really tune them in there. But it tunes in fine at 3810, 3811, 3812. There he is. 13, 14. Not 16. Not really too much on 15, but I go back to 14. Anyway, you can see that over a fairly wide range tuning of the main tuning control, by adjusting the BFO either up or down, I could tune in the signal. I originally thought that this BFO control kind of one side was USB, one side was LSB, but that's not the case. And this is kind of a different way of tuning a shortwave receiver, different from what I'm accustomed to. But anyway, I'll show you in the next part of the video how I figured out what's going on inside this receiver. It's kind of interesting, and it has implications for the architecture of dual conversion receivers with this kind of 1 kc display, also that need to be able to tune both AM and sideband signals. Okay, here's a very simplified block diagram of the DX390, also known as the ATS-818 from Sanjin. I've really only shown the filters, the mixers, and the oscillators. Obviously, there's a lot of amplifiers in here too, but just to keep things simple and to explain the tuning problem that I showed earlier, I'll just use this diagram. It is a dual conversion or a double conversion superhet. And that means that there's an additional mixer here. So when a signal comes in, say we have a 14 megahertz signal upper sideband coming in, it first passes through a high pass filter and a low pass filter, and then it hits the first mixer. The first mixer up converts, moves that 14 megahertz signal all the way up to get through the first filter, which is center frequency of 55.845 megahertz. Now to do that, we have a phase lock loop digital VFO from the early 1990s running at between 55.995 and 118.780 megahertz. And what you're doing here is with the main tuning dial, when you turn that main tuning dial on the DX390, you're changing the frequency of this so as to allow all kinds of different frequencies as you tune the band to be presented at the 55.845 filter frequency. In this case, to tune the 14 megahertz signal, you would have to turn the dial and come up with a frequency out of the VFO of 69.845 megahertz. 69.845 minus 14 megahertz equals 55.845. We've taken the difference frequency coming out of the mixer. Now, the reason that they do this up conversion, is it takes care of one of the main problems of the superhet receiver, and that is images. So there'd be another frequency that if it was coming in here could come through and produce also 55.845. And that frequency turns out to be 125.69 megahertz. So if you had 125.69 megahertz coming in here, and it combined with 69.845, that difference frequency would be 55.845, and that would also get through. But it's very easy to come up with filters here that will knock down a frequency that high. It's not close. The other image frequency is much, much higher at 125.69 megahertz. So a low-pass filter, say, set with a cutoff frequency of 30 megahertz, is going to completely eliminate something that high. So you're going to take care of the image. Anyway, this is what's tuned when you change the main tuning dial. Then it goes to the 55.845 megahertz filter, and now it goes to the second mixer. And here's where things start getting interesting. What we're doing here with the second mixer is we want to take this VHF signal at 55.845 and move it down to the 0.450 megahertz or 450 kilohertz range, where we have two ceramic filters that are much more selective, that can provide the needed selectivity for this receiver. One is wide, one is narrow. This is good for AM, this is good for single sideband. What we do is we have another mixer. Here we take a signal of 55.395, which is just 450 kilohertz below this frequency. This signal comes in, combines with this one, and boom, you have 450 kilohertz coming through one of the filters. Now, the interesting thing that I found was that when you move that BFO tone control, that control that I showed you earlier that you saw me adjusting, you're not really changing the BFO frequency, which we'll discuss in a second. What you're doing is you're changing the frequency of this oscillator. You're moving this oscillator up and down a bit. And that has some interesting implications as we go through it. But anyway, let's just talk it through. It goes through, and the 450 kilohertz signal then goes through the filter. And here's where you have the BFO. You have a BFO frequency set fixed at 450 kilohertz, right at the center frequency of the passband of this filter. Now, I've drawn the passband of the filter down here, a rough depiction of the passband, 450 at the center, -2 +2. So 448, 452 here. And let me show you what happens when a single sideband signal comes through this receiver. I have a little single sideband signal drawn up for you here. So this is would be like an upper sideband signal coming through, and you can see as you tune it, you're tuning it here. This black line is where the suppressed carrier should be. So to have this audio sound correct, sound human, you would have to have this thing lined up exactly with the 450 hertz signal. Now, what you could do here, for example, suppose you tuned it with your main tuning dial, but you ended up with this. This line is not lined up with the 450 hertz. Your main tuning dial, and you're hearing Donald Duck sounds. It doesn't sound natural. But then you grab that BFO tone control, that control that's down here, and you move it. So even though your main tuning dial remains fixed, because that BFO control controls this frequency, you're moving it up here. And that's why, as we demonstrated in the first part of the video, even as you move the frequency, the main tuning dial up and down, you're still able to tune in over a certain range the signal to make it sound human. Now, this works also if you have a lower sideband signal. Here's a lower sideband signal coming through. Same thing. If it's up here, even if you don't touch anymore the main tuning dial, you say, okay, I'm going to move it down here. Boom, I'm going to get it right there. Boom. Now it sounds good. Now it sounds human, even though the main tuning dial is moved. And this creates a bit of a problem because only at one setting of the BFO will the main tuning dial accurately reflect the frequency. And when we talk about frequency with single sideband, we're talking about the frequency of the suppressed carrier. So you have to be conscious of that when you tune a receiver of this nature. Now, why would they do it this way? Well, I think for a few reasons. First, the phase lock loop that you have as the main oscillator in this receiver and the display is limited to 1 kilohertz kind of integers or intervals, right? So if everybody on a band was transmitting on exact 1 kilohertz intervals, as is the case often on, say, 40 meters, it would work out okay because you would just tune it. You would tune the main tuning dial, leaving the BFO fixed until boom, you're right there. But what happens if somebody is not on the full 1 kc integer interval? And suppose they're transmitting between two 1 kc marks. Then you would tune it, and it would still be off. It would be sounding a little Donald Duckish. So you'd have to move it with the BFO control to get it tuned in. That's one reason for doing it this way. The other reason, I think, is that this is a shortwave receiver, and it's also designed to receive AM. So what you could do if you were receiving an AM signal, you could just turn off the BFO. You could turn it off, and this BFO signal, the 450, would not be there. The AM signal, which would be on both sides of the 0B, would fill up this whole thing, would then go through an AM detector, and out it would come. I hope I've explained that right. It's a little bit complicated, but it's interesting, and it was kind of fun to go through and try to figure out why these receivers were working the way they are working. Anyway, I hope you enjoyed the video. It is an interesting thing to explore different receiver architectures. 7-3.